All right, so we're going to work in our chapter 4, which goes over models of atoms. We're going to take some of the highlights and information from those models and apply them to how we interpret the modern atom. As well, at least in our introductory chemistry class, and also in future chapters, we will rely on this information to help us understand things like bonding. So I'm breaking up the chapter into different sections, trying not to make any one section too long. I will go through it in the same order that it is in your textbook. So once I stop, I'll start and go to the next topic on another video. We're going to start before your book even starts, and that is to look back at early Greece. I'm not asking you to memorize anything that is on this video. I always just like, though, to, before we jump into the 1800s, understand that people have been thinking about matter, what's around them, how it goes from one form to another, for a long time. And so often in terms of Greek philosophy, we do have things that are written down and recorded that we can see what they were thinking. And I've chosen these because they were thinking about elements, so it's specific to chemistry. So if we look here in the 400 to almost 500 BCs, Empedocles, he proposed the idea that matter was just 4 elements: earth, air, water, and fire. And those 4 elements, forced through forces like love and strife, could mix and separate, and then that would form different things. And that's how everything around us was formed, which now we kind of scratch our heads at. But I read other things about how he was thinking about it, and it's not crazy. Like you think, oh, okay, I could see how they might interpret it that way. Then comes along Democritus, and he starts thinking more along the line of how we might think about modern atoms. In fact, he named his little particles atomos, which means atoms or indivisible in Greek. And so he instead proposed the idea that matter had small little individual particles. Now, he wasn't thinking about elements like we think about elements, but he was thinking of small particles of matter that couldn't get any smaller, and those particles together would make the big things that we see. Now, here's a kicker for you. Aristotle, so he was very influential at the time, and he argued that matter and motion are continuous, not discontinuous. So you wouldn't have small little particles of matter like the atomos that proposed by Democritus. Instead, you could just keep dividing matter smaller and smaller and smaller and smaller and smaller. In his reasoning, he supported the ideas of Empedocles over Democritus, and so that those ideas were perpetuated longer. So so Aristotle's influence kind of drove thought in one direction. So again, on this slide, you don't have to memorize it. If you're curious, you can look up some of the ideas about these different philosophers in relationship to matter. But I just kind of wanted to know, like, philosophers were thinking about matter. So now we're going to jump almost 2,000 years here to Dalton's theory, which is going to be in the early 1800s, and we're going to look at Dalton first. I did want to include this slide. So this is an illustration that I found online through this compound interest website. It has all sorts of different things, but I loved how they put this together with some of the things you can look at the bottom, like some of the positive things, the red line, or things that we know are actually true now that they didn't know at the time of the model. And so I have this also in your Canvas shell. And oftentimes in class, I'll print it out and hand it out. So we're going to jump in to Dalton, which you see there, a little solid sphere model. I love this handout for that. So refer back to this after we get through all the models so you can kind of have this abbreviated comparison. So Dalton, and remember what a model is, it's a theory. So it's based on a collection of facts and information. And then you put the theories together to try to explain and predict. And so Dalton's model was trying to explain and predict what they were seeing. And so this is the idea of the atom. Now, one of the things that he gets credit for is that he was trying to distinguish between a fundamental particle, which we'll call the atom, and a compound, which are molecules. So he was distinguishing between those two different things. Now, there are several things in Dalton's model that we would have to adjust if we were going to keep it. And in a future slide, we'll talk about the things that we now know would have to be adapted. So I'm sure Dalton didn't write 5 points for his model, but here for our purposes, it's written in 5 points. So number 1, an element is composed of, you see here, tiny, indivisible, indestructible particles called atoms. So here was his definition of atoms. They're small, they can't get smaller, they can't be destroyed, and we're calling them atoms. Number 2, he said atoms of the same element are identical and have the same properties. So as an example, he would say all carbon atoms are the same. So that's just a way to make it a little more specific. This is just an example. Okay, and then number 3, atoms of different elements form to form compounds. So I think 2 things here. I think different elements. So like what they're saying is, okay, so hydrogen is different than oxygen, right? So they're not the same. So we have 2 different elements, and they come together to form compounds. So for example, hydrogen, oxygen can form water, which has a formula H2O. And I know I use water a lot at the beginning of class because many of us are familiar that the formula for water is H2O, and we'll get into a lot more formulas, but I kind of rely on water to help us in this time when we're first starting to learn about it. Number 4, atoms combine to form compounds in simple whole number ratios, and I kind of already wrote an example of that. So here's water, which water has a ratio of 2 hydrogens to 1 oxygen. So that would be a simple whole number ratio. Remember from the beginning of the course, we have theories which can change if we get more information. We know the model of the atom has changed as we got more information. But then you also have natural laws, which are natural phenomena that under a certain set of conditions are always the same. And the law of constant composition, so the recognition that, for example, water always had the same properties, water was always water, was included in his model. And then the second natural law that was included is the law of multiple proportions. And what that is saying is that 2 atoms can get together in more than one way. And so examples, water is H2O. So 2 hydrogen and 1 oxygen, but hydrogen and oxygen, if you give a 1-to-1 ratio or 2 hydrogen and 2 oxygen, you get hydrogen peroxide. So he was just saying that, sure, atoms get together in whole number ratios, but 2 atoms many times can get together in more than one ratio, and if it has a different ratio, it has a different compound. So a lot of these might sound familiar because we still rely on some of the tenets of his model. On the next slide, I found this illustration, which is, these are the same things that were on a previous page, but they just illustrated using circles some of the ideas. So for some of you, it might help to see this. So this is not different information. It's just an illustrated view. So the first bullet point just says atoms are individual particles which are different for each element. So if you look here, they've drawn the atoms individual from each other, and the oxygen, which is the red ones with the O, are larger than the hydrogen. That's just one difference we see in this illustration. So they're individual. And then on number 2, they're saying, okay, they come together in fixed whole number ratios, and they're showing you here water. So they have 1 oxygen, which is bonded to 2 hydrogen. And then here it's saying that, okay, but oxygen and hydrogen can get together in different ways to form different compounds. And they give you an illustration of the hydrogen peroxide. So this is not new information from the previous slide, just has a little illustration for those of you who that might help kind of get it into your imagination. I found when I was first learning chemistry, these kind of things helped me to get things that I cannot see. An illustration kind of helped it get into my imagination so I could work with it a little bit better. Now, there are some drawbacks, or I would say some things that we now know are not true. These are 3 that are directly impacted by. In your textbook, they include 2 more, a little more advanced things that we won't encounter in our class, but things that we will notice in the theories as we move forward. So we know that atoms, Dalton thought they couldn't be divided any smaller, but we now know there's things called subatomic particles, which we'll talk about in this chapter. I do want to emphasize, though, that when we're talking about atoms, for the chemist, it really is often referred to as the smallest form of matter. Let me give the caveat. It's the smallest form of matter that has a chemical reaction. So there's smaller things, and in physics, there's things inside the atom that they think about a lot in terms of atom formation and all sorts of things, and we will think about 3 of those, the proton, electron, and neutron. But in terms of reactions, the atom is the smallest form of matter that gets involved in that. Now, number 2, they thought that all atoms of the same element were the same. They thought all carbon were the same. But no, what we're going to discover in this chapter is some atoms of the same element are not the same. So I'll just put a little example, and we'll go in detail in the future. My example is not all carbon atoms are the same. They're called isotopes, and we'll learn more about that. We've got to learn a little bit more about subatomic particles, but we'll see how this model gets a little changed. And then number 3, this theory doesn't explain things like allotropes. And allotropes are, for example, carbon can get together with itself and form have different chemical formations. So carbon can get together and form charcoal. You can see there graphite. Diamond is a form of carbon. And the Daltons model doesn't explain this. And I would only imagine that perhaps they didn't know that these different substances were actually all forms of carbon. They didn't have all the ways of detecting some of these things yet, so they probably didn't know, and so it wasn't accounted for or included in the model. So this is Dalton's model. This is where we're going to start. Just as a reminder, in terms of testing, I, in general, don't ask you just to list anything in a given model. What I would expect you to do is to be able to identify things that are in the model or are not in the model, things that might not be true in this model now that we know are different. So things like that, but I won't. So I guess what I'm asking you to do is, in a big picture, don't worry just about memorizing number 1 is, number 2 is, but try to incorporate a larger picture of what the model is contributing, and then where that model has deficits or where it has needs changes for what we know now. So we're going to be going over, if we look back here, in our next video, we're going to be looking at Thompson and Rutherford. So we're going to take a look at those 2 models in the next video.